molecule with the formula C4H9Cl is analyzed. That's probably going to be a haloalkane. The proton NMR spectrum of this molecule is shown. What is the structural formula of the molecule? Okay, so first things first, you want to know what information you get out of your different spectrums. Okay, for an NMR spectrum, you get out chemical shift, which is it downfield to the left, or is it upfield to the right? If it's downfield, it's close to an electronegative atom. If it's upfield, it's far away from an electronegative atom. So that's what chemical shift tells you. So left is downfield, right is upfield. Number two, it gives you information about integration, which is how tall the peak is, okay? How tall the peak is will tell you how many different protons, in this case, it's a proton NMR, or if it's 13C NMR, it'll be how many carbons. It'll be, integration tells you how many protons or how many carbons have the same chemical environment. And from last lesson, what we said is that the chemical environment is, pretend that you're standing on the molecule and then rotate yourself around, just walk around in a circle on that single atom, yeah? Does the molecule look the same from where you're standing? If the molecule's symmetrical, if your methyl group can rotate, you're going to see the same thing. But if you're rotating and from this molecule, and from this atom, when you're standing on it, it looks slightly different to when you're standing on the other atom, then the chemical environment isn't the same and it should produce more than one signal. So if it produces the same signal, then that means that those different atoms show this look. From those different atoms, the molecule looks the same. Okay, so that's what chemical environment is. When you're standing on that atom, does the overall molecule look the same? That's what integration is. And then number three is splitting. Splitting shows you the number of neighboring protons. Okay, so to summarize, chemical shift gives you information about whether or not it's close to an electronegative atom or far away. Integration gives you information about different atoms and whether or not they look the molecule looks the same from standing at those different atoms, which means when you rotate, when you stand on your different protons or when you stand on your different carbons, does the overall molecule look the same? If the overall molecule looks the same, then those different carbon atoms or those different hydrogen atoms are going to create a signal at the same point. That point is going to go higher and higher. Splitting gives you information about neighbors, which means I'm standing on this carbon. How many hydrogens are on the carbon next to me? How many hydrogens are on the carbon to the left of me and to the right? So in that case, in terms of splitting and in terms of neighboring, think of it as the hydrogens live inside of the carbons, yeah? So you're going to look at your neighbor on the right. How many hydrogens are there in that carbon house? On the left, how many hydrogens are there in that carbon house on the left? So that's what splitting shows you. Now, splitting is something that you'll only see on a proton NMR. You're not going to see it on a carbon-13 NMR. There is an explanation for this. You can have a read of it in the notes if it interests you. It's quite interesting, okay? It's not necessary for your theory, but it's always good to delve into this a little bit more, yeah? So splitting is only something you'll see on a proton NMR, never on a carbon-13 NMR. Okay, so look at those three things and then have a look at your spectrum and get information out about it one at a time, yeah? So first things first, C4H9Cl, okay? This is your electronegative atom. So first things first, chemical shift, you only have one signal that's upfield, it's to the right. What that tells me is that the protons in my NMR spectrum, they're all pretty far away from my chlorine, okay? They're not that close to it, which sort of implies that the carbon that my chlorine is bonded to, there might not be any hydrogens on that. Okay, so just to reiterate, chlorine is electronegative. If a hydrogen was next to that, the signal would be downfield. But because the signal's further upfield, what that tells me is that the hydrogens are pretty far away from my chlorine. And now you might be wondering, you're like, there's 9 hydrogens in there. How could there possibly not be one close to my chlorine? It could be that the chlorine is bonded to our carbon, and then the hydrogens are all bonded to the carbons that are bonded to that carbon. What that means is the carbon that's directly bonded to your chlorine, there might not be any hydrogens bonded to that. So the hydrogens bonded to a particular carbon might have another carbon separating it from the chlorine. So this is your carbon chlorine. You probably won't see this because the signal's so upfield. It's probably going to be something like this. This is the carbon containing my hydrogen. There's one other carbon separating the hydrogen from the chlorine. Yeah, that could be the situation. Okay, so that's chemical shift done. Number 2, integration. There is only one signal. There is no other signal. A signal gets created at a certain chemical environment. If there is only one signal, there is only one chemical environment. What that means is all 9 of my hydrogens, they have the same chemical environment, which means regardless of whichever hydrogen I stand on, when the molecule rotates, everything looks the same from each 9 of my hydrogens, which means when I go to pick my molecule, this is easy because it's a multiple choice question. I need to pick one where the 9 hydrogens, the molecule is symmetrical around my 9 hydrogens. So even when I rotate, the overall molecule looks the same. So that's integration. Number 3, splitting. Because all of my hydrogens show one signal, there is not going to be any splitting. Okay. What that tells me is because there's no splitting, my hydrogens have no neighbors. Okay. My hydrogens have no neighbors. What that means is, remember, neighbors are the hydrogens in the carbon next to my house. Okay, so just to reiterate, I live in a carbon house. My neighbors are the hydrogens in the next carbon. Yeah. So if my hydrogens, my signal shows no splitting, what that means is the carbon that my 9 hydrogens are attached to, that carbon that they're all attached to shows no, has no hydrogens attached to it. Okay, so to reiterate, I'll slow down on that. Splitting is created by neighboring hydrogens, yeah? Splitting is created by neighboring hydrogens. My single signal has no splitting. What that means is the carbon that my hydrogens are bonded to, the carbon next to it, okay? So my hydrogen is bonded to this carbon. The carbon that's next to it is bonded to no hydrogens. Okay, so to reiterate, my hydrogens are bonded to this carbon. The carbon that carbon is bonded to has no hydrogen. Because I show no neighbors, I show no splitting. So that's my 3rd thing that I'm looking for. So integration, same environment for all 9 hydrogens. And then splitting, no neighbors. Okay, so what that means is the carbon that my carbon, me is a hydrogen, by the way, the carbon that my carbon is bonded to has no hydrogens. Because if it did have a hydrogen, that hydrogen would be my neighbor. Okay. Can I get a thumbs up to confirm that that makes sense so far? Do we have any questions? I'd love to address them now so I don't let your confusions carry on. Grace, makes sense? Good. Jen, makes sense as well. Awesome. That's the kind of thought process you want to go through every time you're interpreting a spectrum. Do not, and I specify this, okay? Do not look at your molecule first. And then if it's a 8-mark question, pray to Lord, do not try to interpret the spectrum. Sorry, but do not try to predict the structure of the molecule without going through step-by-step chemical shift, integration, and splitting for your spectra. Yeah. Look at the spectrum first, figure out the structure after. Don't try to look at those 4 options and then link it to each of the spectrum. It takes a really long time because then for each molecule, you'll have to go chemical shift, integration, splitting. And then for the next molecule, you have to go chemical shift, integration, splitting. So it's easier to go chemical shift, integration, splitting, and then just apply to each one of your 4 options. Okay. So let's have a look at this. Molecule 1. There are, first of all, check that the formula fits. Okay, the chances of them giving you a molecule that doesn't fit the formula is unlikely, but it's very possible, so you want to watch out for that. So there's 4 carbons, 9 hydrogens, 1 chlorine, all good. Chemical shift, it's further upfield. Notice how the carbon that's directly bonded to your chlorine, there's no hydrogens on that. Every hydrogen is bonded to a second carbon, which is a carbon that's 2 carbons away from your chlorine, yeah? So the hydrogens are relatively far away from your chlorine, so it makes sense that it's upfield. So this one, let's give it 3 ticks, yeah? It gets the first tick. And then number 2 is integration. Do the hydrogens have the same chemical environment? Okay. Now, what I like to think of it as is stand on the molecules, see what everything else looks like, and then use a reference point. Yeah, normally the reference point is going to be like an oxygen or a chlorine or a halogen, just so it's really easy to figure out what the molecule should look like. So these hydrogens right here, by the way, when hydrogens are in a methyl group, like a CH3, all 3 of those hydrogens are going to have the same chemical environment because they're single bonded to a chlorine, which means when you rotate it, everything looks the same. Okay, so what we said last lesson was don't think of your single bonds as stagnant points on the page. This chlorine can rotate, yeah? So in like t+1 second, this hydrogen could be over here, this hydrogen could be over here, and then this hydrogen could be over here. So in a methyl group, the carbon can rotate. So then everything will look the same, yeah? So these hydrogens have the same chemical environment, these hydrogens have the same chemical environment, these hydrogens have the same chemical environment. Okay, however, the methyl groups are all bonded to the same carbon. Okay, the methyl groups are all bonded to the same carbon, which means this carbon right here can also rotate. Okay, so this carbon's going to rotate, which means similar to the hydrogens here, this methyl can rotate over here, this methyl can rotate over here, this methyl can rotate over here. So because they all go around and they eventually reach each other's positions, everything in the molecule is going to look the same to each methyl group, to each hydrogen in each methyl group. So each hydrogen in the 3 methyl groups are going to see the same thing as the carbon rotates around. So each of these hydrogens are going to have the same chemical environment, all 9 of them. So in this case, they're all going to produce one signal because everything looks the same from them. So it's upfield and it's the same signal, 1. And let's see if they're splitting. Okay, so splitting is for the neighbor. For this hydrogen right here, it's bonded to this carbon. This carbon is bonded to no hydrogen, so no splitting. And then the other methyl groups are bonded to the same carbon. The same carbon that has no hydrogens. So all of them are going to have no splitting, which means A fits your criteria for all of them. Can I get a thumbs up? Does that make sense to you guys? If we have any questions, by the way, about the integration and about the same chemical environment thing, I'd love to hear your question so that I can tell what's confusing in terms of a student that's studying it for the first time. Yeah, it'll be really interesting because I know that chemical environment thing is a little bit difficult to grip your head around, and it's sort of a matter of doing a bunch of different questions and then eventually getting your head around it. Yeah, so whatever questions you have, please pop it down for me because it'll help you, because I'll be able to answer your question, and then it'll also help me figure out what's confusing about it so that we can explain it clearer in the future as well. Okay, so let's have a look at the other ones first though and see why they wouldn't fit the spectrum. Yeah, in B, this carbon that's directly bonded to this chlorine has hydrogens on it, which means these hydrogens right here are way closer to the chlorine than the other hydrogens are. So this one would actually be relatively downfield. Okay, that's the first thing to watch out for. The second thing to watch out for is that because the molecule is not symmetrical, the carbons are in a line. Normally, by the way, when the carbon's in a line, it's not going to show one signal because they're a certain distance away from something. They're not like they're equidistant. So this hydrogen's going to show one peak. This hydrogen's going to show another peak. These hydrogens, however, are both attached to the same carbon. So they're not in the same line anymore. They're attached to the same carbon, and this carbon, once again, can rotate. So this is going to be 1 peak, 2 peak, and 3 peaks. And this one is, that third peak is going to be integrated a little bit higher. Yeah. And then this one does have neighbors. This first peak has 1 neighbor, so it's going to be split into 2, a doublet. This one right here, this hydrogen has 3, 6, 7, 8 neighbors. So it's going to be split into 9, which is what, like a nonnet? Or I don't actually remember what the prefix for 9 is. You guys should let me know if you know what it is. But it's going to be split into 9. And then these methyls right here have 1 neighbor only. So it's also going to be split into a doublet as well. Okay. And then for option C, this one's going to be downfield because it's directly bonded to the carbon, bonded to the chlorine. And then because the molecule's asymmetrical, this hydrogen's going to show 1 signal, this hydrogen's going to show another signal, this hydrogen's going to show another signal, and this hydrogen's going to show another signal. So that's going to be 4 signals. Yeah. Now you might be wondering, these methyls at the end look the same. Okay. However, this hydrogen is 1, 2 spaces away from the chlorine, whereas this hydrogen is only 1 space away from the chlorine. So it's also not going to see the same thing. Okay, so it's not going to look the same because the chlorine is going to be closer to one end than to the other end. And then for D, this hydrogen is going to be the most downfield, and then it's going to eventually go upfield. This one's going to be the highest upfield because it's furthest away from your chlorine. And because it's in a line with a chlorine at the end, the molecule is asymmetrical. So each of these hydrogens are going to show a separate signal because from each of the hydrogen, the molecule looks different. This hydrogen right here is 1 position away from the chlorine. This hydrogen is 2 positions away. This hydrogen is 3 positions away. This hydrogen is 4 positions away. So from each of your hydrogens, they're a different position away from the chlorine. The molecule looks different standing on each of them. So each group of hydrogens is going to have its own peak. Okay. However, the hydrogens that are bonded to the same chlorine, the hydrogens that are bonded to the same carbon. So in this example right here, for example, here, what it actually is the hydrogens bonded up here, and then the hydrogens bonded down here, and then likewise like this. So these hydrogens can rotate around the same chlorine. So just rotate around in a circle like that, which means for these 2 hydrogens, they do have the same chemical environment. Okay, so think of it in terms of this. If you have hydrogens bonded to the same carbon, they're going to be in the same chemical environment. And then if the hydrogen is bonded to a carbon, and that carbon is bonded to another carbon, which is bonded to every other carbon, then all those different hydrogens are going to be also in the same chemical environment. So what I mean is, these 2 hydrogens are bonded to that carbon, they're going to have the same environment. These 2 hydrogens are bonded to this carbon, they're going to have the same chemical environment. However, this hydrogen and this hydrogen are bonded to different carbons. So even though 2 and 2 have the same environment, 2 and 2 together, the 4 of them do not have the same environment. Unlike this one up here, these 3 are bonded to the same carbon, same chemical environment. These 3, same carbon, same chemical environment. These 3, same carbon, same chemical environment. However, the carbons are all bonded to the same carbon, which means the hydrogens must also have the same chemical environment. Okay, so basically, in terms of chemical environment, the trick for you is see if they're bonded to the same thing. If they're bonded to the same thing, they're going to have the same chemical environment.